We've just finished learning about butane and ethane and how there's rotation around the single bonds between those carbons. We've drawn Newman projections and seen how there can be staggered or there can be eclipsed conformations. Now I want to take that into a bigger system and look at how this affects one of the most common rings in organic chemistry, cyclohexane. So cyclohexane is a really common ring in organic chemistry. Cyclohexane can form something called a chair conformer. And that's what we're going to talk about today a little bit and the reasons why. So if you draw cyclohexane, cyclo means that it's a circle of bonds. So we have carbons bonded like this. Notice it says hexane. Hex means 6, right? So there's 6 carbons. And since it's just an ane ending, that means that these are just filled with hydrogens. There's nothing but hydrogens attached to each of these carbons. Now, as we're looking at this, we probably notice that there's some weird angles going on here, right? Because if this was all in flat planar space, each of these angles would be about 90 degrees. Well, we know that that would not be good with Weissenberg theory or valence shell electron pair repulsion theory. Those things want to get as far away from each other as they can. And we know that forms a tetrahedral structure on carbon, so usually 109.5 degrees apart. Well, is there a way that we can maneuver all of these to be in that position, but also to be staggered? So to do that, what I'm going to do is I'm going to start by talking about some Newman projections. Now remember, Newman projections, we usually look down. Let's say you had like a butane like this. For Newman projections, we would look down. We'd look down one of these bonds, and we would say, hey, if we look down that bond, we would essentially have something like this, where we would have a front carbon with some things attached, and then we would have some things in the back like that, for example, if it was staggered. And of course, in this case, 2 of these would be hydrogens and the other one would be a CH3. And on this one, we'd have hydrogens and a CH3, and this would be anti-position. They're opposite from each other, those large groups. So this would be an anti-position, and it would be staggered where they're sort of in between each other. So that's the general idea we get here. Well, now let's take this into a more complex cyclic compound. If we look down these bonds, here, and we look down this bond here, what we're going to notice is that we get a really interesting Newman projection if they're in a flat plane. So let's go ahead and draw that. So let's say they're in a flat plane. I'm going to draw these 2 next to each other. So imagine that our eyes are now looking down. Instead of looking over this flat cyclic compound, we're now looking down in line with that flat cyclic compound. Well, what does that mean? Well, it means we're going to have this, right? This is carbon 1 right here. Let's draw this one's number 1, right? So that's right here. And then we're going to have an eclipsed bond in the rear, right? So this is eclipsed bond in the rear. And this is going to be, if we number this around, 2, 3, 4, 5, 6, this back here is going to be bond carbon number 4. So see, those are eclipsed. Well, if those are eclipsed, we know that all of these other hydrogens must also be eclipsed. So where would those hydrogens be? Well, in the rear. And then in the front, like I said, those are all eclipsed. So what we're going to have is something like this. And these are all eclipsed with each other, all right? So this looks really, really high energy. This is not great. And by the way, just so we have talked about this, we have number 2 carbon here, 3 is in the back, 4 and then 5 here is in the back, and then 6 carbon is right here. So kind of walking around the ring in that way. Now, what if instead of, as we noticed, these eclipsed things are not good, they're very high energy. What if we wanted to go to a staggered position? Well, to do that, let's just go ahead and take this carbon and move it down, and this carbon and move it up, right? So as we move this carbon down like this, we're sort of bending everything in this way. And so what that's going to do is rotate all of this. So let's go ahead and redraw that. So this is taking the exact same molecule, but putting it in a more favorable position. Well, now we have our CH2 down here. We have our other CH2 back up. Sorry, my mistake. That's in the back, right? So actually, I should even change the color. Right? And now let's put our hydrogens in here, right? So this one's here to make that sort of tripod position. We're going to need to go here and here. Sorry about that one. Here and here. And then if we get, so those are hydrogens. Now if we put our other ones in, and there we have our Newman projection of the most stable conformation, right? Because now these are all staggered. And if we pay attention, we'll actually notice these are all also about 109.5 degree angles. So this is our Newman projection of the chair conformer. Now, what do I mean by chair? Where do we get the word chair from? Well, if I was to redraw this, what you'll notice is that we have these 2 carbons bonds that we're looking down. So if I'm to draw those 2, they kind of would draw a bit like this, right? Okay, so let me just move this one a little bit, maybe more to right about here. And I do want to do one more thing. Let's just rotate them a little. This will make my life a little easier for our chair. So let's say that those are the 2 even frame rails right there. Now, in the front, you'll notice it kind of tilts down to this other carbon here. So how would I put that in here? Well, let's put the part that comes down. And then we sort of have a part that comes up in the back here. So let's go ahead and throw that in. So that would look a little something like this. Okay? So if you imagine this is kind of a chair here, because it has sort of, imagine that flat ring, and we creased it here, and sort of bent that up, and creased and bent this part down. If you imagine it as a chair, here's a person kind of lounging in the chair, right, with their feet there and their hands here, they're holding the drink right here, right? So that is sort of how you could imagine that as a beach chair almost in a way. Well, what if we were to put all of the hydrogens coming off of this? Where would those hydrogens go? So I've taken the time here to draw a chair conformer a little more carefully, and I want to look at this chair conformer and sort of look at some properties that come out of being a chair conformer. So here is our chair conformer. And if you notice, I used a couple different colors, and I sort of shaded here. I'm not the greatest artist, obviously, but this right here, I made that a little bigger because that is more closer to us, and the one over here is behind, right, to give you that three-dimensional aspect of the chair. The other thing that I did was I colored the red and the blue hydrogens a little differently. So just so we can all be on the same page, let me move this down here. So we can all be on the same page. These are all hydrogens. They're all the same, of course. And what we notice is that they're in different places, and I've used the red and blue to sort of delineate these. So what we'll notice, if you look carefully, is that all of the red hydrogens are pointed either up, straight up, or down. So if you imagine this cyclohexane as a flat thing, which it really isn't, but if you imagine it sort of as this flat space, we have these hydrogens coming up and down from it. You have these hydrogens coming up and down from it, and then you have these other hydrogens that are sort of coming out from it. You notice that this one's sort of pointed out like this, and this one's out. They're all out. So if you build this model as I've recommended, and then look from the top, you're going to notice if you look from the top that there are hydrogens coming at you and away from you, right? And we call these hydrogens in this direction, like up and down like this. We call these axial hydrogens. And then we have other hydrogens that are coming out like this. And those we're going to call, they're kind of along the equator here. So we call those equatorial. So we have these equatorial hydrogens coming out like from the equator, and these axial hydrogens coming up and down. And so where do you think it would be better for the hydrogens to be? What's the most stable position? Well, these axial hydrogens, because they're coming straight up and down like this, are going to actually interfere with each other. So we actually call this 1,3 diaxial interactions. So these are going to, right, because if you look at right here, there's 1, 2, 3 if we number around like this. These are 1,3 diaxial interactions, and they actually take up some space and push against each other there, right? Now, if they're all hydrogens, this doesn't matter. But what happens when we get something really large there? So let's say that instead of just hydrogens, we have a methyl group, 2 methyl groups, one here and one here. So we now have a substituted cyclohexane. Well, does this look good? No, because those CH3s are rather large, and they're going to be pushing against each other here, repelling each other. We call that steric hindrance, right? They're pushing against each other. And what that's going to end up doing is creating diaxial interactions and making this conformer not that great. Well, why? What could we do differently? Well, I want you all to pause the video and do me a favor. Take your cyclohexane and take your footrest and twist it up into a headrest, right? This would be like boat. And then take the one that was a headrest and twist it down into a footrest. As you do that, pay careful attention to what happens to all these substituents. In this case, our 2 methyl groups. Go ahead and do that. All right, so what you should have noticed when you did that is everything that's in the axial position actually switches to the equatorial position. Because when you rotate this up, that Newman projection is actually moving all of these to be eclipsed, and then we keep moving until they're staggered again. But in that entire movement, what we actually do is we move everything. I'll go ahead and show you real quick. Essentially, my very quick drawing here. What we're going to have is this methyl right here is now going to be going back out like this, axial, and at the same time, this methyl on the footrest is going to be coming out like this, axial. then we're going to have all of our hydrogens, of course, will not have switched positions, but I will draw this hydrogen is now going to be axial down, and this hydrogen here will be axial down. And interestingly enough, these will be having 1,3 diaxial interactions. The difference is now it's a small group like a hydrogen instead of this larger group. So what we're going to see is that as we move groups, we actually have energy changes that make it prefer one conformer or another. Now this really matters because in reality, these different conformers are all in equilibrium with each other, right? So if we looked, this would actually be forming an equilibrium between the two in solution. Now which one would it prefer? We know it would prefer the one below here because it will put the larger group in the equatorial or low energy position. Now, you're going to practice this because as you move certain things, sometimes it might move a methyl in one place, but it might move a bromine into the axial as we move a methyl into the equatorial. Now, which one of these would it prefer and how does that affect things? We'll see how it affects things as we move on in the future.